name is Luca Deri. I am the founder of this open source project called Ento. I started almost 20 years ago. And I use Wireshark since a very long time. It has been very helpful. Because when you have to monitor network traffic, the first thing you have to do is to have the code, the traffic. So you have to know what you are receiving. And Wireshark is more than an helper for us because it allows us to understand what's going on and what is happening. But contrary to what I've seen in many talks and sessions here, we are not really packet-oriented people. For us, packets are a way to transport information, whereas people that are using our tools are looking at the overall picture. So they want to understand what's going on. So looking at one packet, it is interesting. But on the other hand, it does not give us enough information for understanding what's going on. I think an example is when you have an unknown network. Unknown doesn't mean that you don't know anything at all about the network. But for instance, that somebody comes and asks me, hey, Luca, come to SharkFest. We have a wireless network. We have people coming. Try to understand if people are happy of the internet connectivity. Of course, you can go packet by packet. You can start your Wireshark session, look at the cores. If you see something yellow or red, then start to become nervous. But that is not what we do with network monitoring. In network monitoring, we try to give more high-level metrics rather than being packet-oriented. In fact, in network monitoring, things like IP addresses or port are not very helpful. For instance, today my computer has an IP, but that's not very relevant because this IP can change over time. Maybe if later this afternoon I turn on wireless again, I will get another IP, but it is still me. And at the same time, if I go to Facebook, I don't really care what is the Facebook IP address I'm talking to at the moment. I just know that I'm talking with Facebook. So for me, the main information is that my PC is going to Facebook. And the same for ports. The destination port is usually known. So in the case of Facebook, it will be 443. The source port is not very important because it's a dynamic port, similar to the example I made before with the local language. So in essence, looking at packets, it is very good. But from the network monitoring standpoint, we need to have a global picture, a higher picture. This is problem number one. Problem number two is to understand what's going on. There are so many protocols today on the network that we cannot rely on what the Wireshark decoders are telling us. Simply because they are still looking at the packets from the TCP point of view, from the HTTP point of view, but people are not used to this type of information. If you talk with somebody in the street or in the corridor, or if you talk with a father that has children accessing the internet, he simply wants to know whether the children use Snapchat, just to give an example. They don't know anything about the thin flags. These are things for professionals. I know most of you are interested in this type of information. But what I want to say is that the goal of this talk is to complement what Wireshark is providing you with some higher level information, something that you can use to understand what's going on a network that you don't know, or even if you know the network, to have an idea of what's going on. For instance, these days, if you go to Amazon, if you go to many electronic shops, you will see that there are appearing on the market small boxes. Usually they are about $100 to $200. So you put them in a network, and this box is telling you what is your son doing, or it's time to go to bed. So don't use, let's say, YouTube after 9 p.m., this type of things. And the first thing that those boxes are doing are creating a list of devices that are connected to the network. First of all, because you want to find out if there is an intruder on the network, or you want to see what is your television, smart television is doing, if it is connected to the network, to the internet, and what. So this is the idea. So in essence, we should move from packet view to a high-level view. In this talk, then, we are going to see a few things. First of all, I'm going to show you how to characterize the network traffic more at high-level protocol, what we call layer 7. So Facebook, okay, it is not a real protocol, it's just HTTPS, okay, so SSL. But for me, it's Facebook. The same for Skype, the same for YouTube, the same for BitTorrent. Some of those protocols are identified by Wireshark already, but they are marked as SSL, for instance. Instead, we would like to see, okay, this is Google DNS. It's not DNS. I'm talking to 88888. Second problem is to capture traffic. If you have your machine connected to the network when you want, that you want to monitor, okay, you can simply turn on Wi-Fi, turn on Wireshark and capture traffic. But sometimes you are not that lucky. Because sometimes the problem is far away, or sometimes the problem appears at an unexpected time. So a typical example is Monday morning when everybody goes to work, and the HTTP is under pressure. So from 8 to 9 to 10, depending on the country, you will see that there is the problem. So you have to go and sniff exactly at that time. Suppose that you're monitoring a mobile network or a large Wi-Fi network like this one. Sometimes there is a problem on a specific place. So you need to do continuous packet recording, and then when your metrics are telling you that there is a problem, then you want to go down to the packet and see what's going on. So what I wanted to say is that it is not possible all the time to turn on Wireshark when the problem happens. But sometimes you have to continuously write packet to disk, and in case something happens, then to go and focus on those packets. And those packets might be remote. So you might be in a different location than the location where the packets are captured. For instance, if we have this campus, we'll probably be deploying several pros here and there. So if you want to monitor the Wi-Fi quality, for instance, you want to set up your Ethernet card in monitoring mode, and you have to be exactly in the place where the Wi-Fi traffic flows. You cannot put that up somewhere near the Internet gateway and hope that you will be receiving there information about the Wi-Fi quality, the signal, and that's assignment. Okay? So in essence, if you have an unknown network, if you have a wide network, the first problem is to understand what's happening in this network. The second problem is to be able to access the packets exactly where they are without moving them to a central location. And the third problem is to have an overview of your traffic. So to start from a bird view, so you understand what are the main things that are not just the dog talkers. Because Wireshark allows you to see many statistics. Beside the statistics menu, there are many things you can already know on this traffic. But still, they are IP and port based. And I told you before that the IP and ports are not that meaningful today. I mean, they are, but up to some extent. So I will be showing you what we have done as contribution to Wireshark in order to use Wireshark as an engine and to turn Wireshark into a more monitoring-oriented tool rather than simply being packet-oriented tool. So we are trying to complement what's already existing in Wireshark that from the monitoring point of view is not yet evident. It is there, but it is kind of hidden. So this is the idea of the talk today. But before starting with the talk, I just want to give you a little bit of an overview of what we are doing. Like I've said, we do a 10 top open source traffic monitoring tools. Open source for us was very important. We heard this morning during the keynote speech that the main developers are using Wireshark. They are developing Wireshark for various reasons. In our case, open source has been very, very important for many reasons. First of all, because we believe on that. So, and when you do open source software development, you also have to reward those communities, those developers that have produced tools that we are using. So in a way, we feel obliged also to contribute to Wireshark and not just to use Wireshark for our own monitoring needs. This is why we are here. And also, throughout the years, we have realized that monitoring per se was an interesting problem. But in order to do comprehensive monitoring, you need a set of tools around it to make it happen. First of all, we need to capture packets efficiently. Because you know that today, networks are going faster and faster. And to have 100 or 1 gigabit network is less and less common. So sometimes you have to capture the traffic on a trunk that is running at 10 or 40 gigabit. So accelerating packet capture is an important thing that we have done years ago with something called PF3. And then later in the talk, we'll be talking about deep packet inspection. Okay, one of the motto of Wireshark is go deep. Yes, we are going deep. So we are analyzing the packet payload because we want to use the packet payload not to spy people, but just to understand what is the higher protocol that we are monitoring. Again, I don't want to say that Facebook is a protocol, but in a way it is an application protocol. So I want to be able to understand on a pie chart what portion of the traffic is Facebook, what portion of the traffic is DNS, and if it's DNS, what DNS am I using? The Google DNS, the Open DNS, the Campus DNS. This is also an important question because it might be that your problem is not in general with DNS, but because somebody has a misconfigured DNS configuration. Maybe this is using a DNS that is not the one that is supposed to be used. And the same for the gateway, and so on and so on. So having an overview of this traffic, especially when you are running at high speed, it is very, very important. And then through the years, we have produced many other tools. So just to give you an idea, all our software, open source software, is on GitHub. So on GitHub, github.com/ntop, you will also find an entry called Wireshark ntop. In this Wireshark ntop, we have the pointers to various modules. A few of them are part of this talk, a few others are not. So in essence, this is a point to the various open source software for Wireshark, to which we have contributed. Okay, this is a quick introduction on ntop. Recently, for instance, just to give you an idea, we have contributed to the NetFlow plugin because we are doing NetFlow traffic monitoring. So for instance, what you have seen today, or we will be seeing today, is just a part of the activities we are doing. And this is because it is important for us not just to use tools, but also to contribute to the tools we like. And so this is an example of our contribution that you can see on the Wireshark GitHub. Okay, so let's start from the beginning again. Problem statement. Wireshark is a good open source packet analyzer. But being a packet analyzer, it is packet oriented. Nothing bad with that. But we need something on top of it. Okay? We need to know, first of all, what is the problem? Before my talk, there was another instructor that was talking about specific problems. And I was noticing that all the examples were short pickup file, where the problem was kind of already known. This is my problem. Okay? No, we are not lucky many times. And sometimes we just know that there is a problem. We know that people are unhappy about specific things, like, for instance, when I said the DHCP is not giving the correct addresses, or the DNS is not able to resolve addresses properly. So therefore, it is important that we also have the possibility of having an overview of the traffic we are monitoring. Because, again, a 50 packet long pickup trace is simply not realistic in general. It is something special that can happen if somebody has already made an analysis. Now, here we are talking about the beginning. So we just go, we arrive here, and we want to see if everything is okay. So we have a little information about this network. And then we have the problem of the speed. So we must be aware that Wireshark is mostly focusing on packet decoding. The fact that the Wireshark is capturing packet, it is important, but it is not the core activity of the application. We have heard this morning the initial port to Windows on Wireshark was unable to capture packets. This was a limitation, I understand. But the core activity of Wireshark was there, because the core activity is to dissect traffic and to show packets. But unfortunately, when you have a high-speed network, and today this is the case, you must also take into account the problem of capturing traffic. That is not so minor. It actually is the first problem. Because if you see a packet drop, then, okay, you'll be receiving a pickup trace full of holes simply because you're dropping some packets. They are not realistic, because if you want to analyze the real traffic, First of all, you must make sure that what you're seeing, what you analyze, is exactly what has passed in this network. So, another thing is high-speed packet capture that is becoming important. And then let's define what is an unfamiliar network. So, the title of this talk. We believe that there are many unfamiliar networks that we have to analyze. First of all, an open network is definitely one of those, where people, you see here, bring your own device. This is a typical example today. So you are coming from your office, from your home, you bring your laptop, and your laptop is configured by somebody else, you take an IP address, you do stuff. And these days, operating systems are very robust with respect to the past. In the past, the operating system didn't do much. Now, if you turn on your PC will start advertising the services it has. You open Chrome, and Chrome is searching for a Google Chromecast machine. You open iTunes, the same story, and so on and so on. So there is a lot of traffic in this network that is not generated by humans, but it is generated by the system you are using, simply because the plug-and-play principle has been extended, and now you see that this is what is happening. Otherwise, you have a temporary network. So this can be an example today, again, this conference. So when you set up a network, there are people coming, a conference, a meeting, or whatever, and then they go. Okay, so you don't know exactly what to expect. I didn't know if today the room was full or half empty or anything like that. So in essence, I cannot set too many expectations on the type of traffic I would see. Otherwise, if you are a consultant, somebody is contracting you, say, okay, come to my office, analyze what's going on. I can tell you something, but I don't want to tell you everything. First of all, because network map is outdated, and second, because of NDAs, and third, because maybe I don't know all the details. So it is up to you to figure out what is happening on our network. So, like I said before, the HTTP is a typical example. So we don't know when we have to monitor the network. Sometimes we are not there when the problem happens. So we have to put permanent monitoring system to capture the traffic, and then using the monitoring tools, we try to find out the time window when the problem happens, and then when we do that, at this point we can use Wireshark, but not before. Because you know that Wireshark is very efficient, but the more it stays up, the more memory it uses, and so on and so on. So Wireshark is not designed to be used as a permanent monitoring tool, but rather than to be used as a monitoring tool when you have already an idea of what is the problem and how you want to track it. So we need to be able to capture the traffic when the problem happens, and when it happens, then at this time we can open a Wireshark and analyze the problem. This is very important. If you look at this window, this is a typical example of Wireshark. Wireshark in this window allows you to capture traffic, okay? And you set, this is the amount of traffic you want to capture. This is for how long. This is the number of files you want to create. So this is good. Again, not for permanent monitoring, but for longer monitoring. But this one is not designed for high speed. It is designed for reasonably good speed. 1 gigabit can work. But today we have, faster network. Also, please understand that it is very important not to drop any packet. Because if you drop packet during packet capture, you will make a lot of assumptions that are not true. Simply because you are looking at a packet trace that is not correct with respect to what has flown to the network. So packet capture is the first important activities. And if you go here, if you go to the vendor showcase, you will see that there are companies that are selling accelerating cards for doing this activity, because it is very important. It's the first thing that you have to do. And then, Wireshark, for instance, does not implement a good indexing system. When you open a pickup with Wireshark, you see it is read one packet after the other. So, if you are capturing traffic, if you have 1 hour long trace, and then you happen to have the problem after 40 minutes, you have to read 40 minutes of packets until you arrive at the part of the pickup that you're interested in. And without having an index, then you cannot really go and move directly to that packet trace. And then there are something I call application protocols that again, they are not real protocols, or they are, let's say, undocumented protocols. A typical example is Skype. This is a protocol that is used by an application, okay, a voice application, a chat application called Skype. This protocol looks to you as SSL-like traffic, UDP, so it does not exist as a protocol. If you go under the protocol column in Wireshark, you will not see Skype. You will see many protocols, but then at the end, this means Skype. And Wireshark, unfortunately, does not tell you that this is Skype. It just says, okay, this is TCP with a certificate, I don't understand. This is DNS towards whatever, Skype, blah, 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 Microsoft.com, but does not say this is Skype. So this is the idea. So we need to understand in advance application protocol and focus our interest on those protocols. Because being packet-oriented, you know very well the application protocol, but that are very common, like DNS, for instance, or mail, IMAP-S. But you don't know the more popular protocol like YouTube. YouTube or Netflix don't exist as a protocol. They are just SSL with special certificates, for instance, but they're very important. If you have a large trace and you have many users that are using Netflix, the first thing you should do is say, okay, forget Netflix. I understand that it is 80% of the traffic, but it is disturbing my analysis. I just want to focus on the 20% of the traffic that is more important. So this is the kind of protocol we are trying to start. Now, in the first part of the talk, I will show you how to do that. But first of all, let me start with this motto from Galileo Galilei. I'm coming from Italy, from Pisa, that is the town where Galileo was born. He says, measure what is measurable and make measurable what it is not. So in essence, the first thing to do is we have to put our metrics, because I said at the beginning, I'm a monitoring guy. We have to put the metrics I know into Wireshark. And then, at this point, I will be able to do my job. I will be able to understand what is going on. So let's make measurable what is not using Wireshark. So, traffic classification, it is very important, because classifying the traffic allows us to understand what we are observing. Unfortunately, when the TCP was designed, the problem was much easier, because, we had very few protocols, and those protocols were rather simple, and most of them in clear text. So you could simply capture the traffic and look at what's going on. The way that the IP guys thought that it was good for classifying traffic was a classification for some purposes. So usually for giving priority to the traffic. So for instance, if you look at the SCP fields, this is good for quality of service. So if you say, this traffic is special because it is voice, it must have priorities up on top of other protocols. So give priority. So the router will honor that thing. But unfortunately, those days are gone. Unfortunately, you cannot say today TCP port 80 equal HTTP. This is what Wireshark does by default, but it's not true. Because many security tools are producing alerts when they see an unknown protocol on an unknown port, or on an unknown port, unknown protocol. So in essence, the fact that you rely on protocol plus port is not a good idea anymore. A possibility is to classify packets using statistics, or the last one is the packet inspection. So, as you know, classification using markers, QoS markers that are decoded by Wireshark, it is good, but it's just a hint, usually for the router. Also, the bits that you have here are very few, so you cannot really put many protocols. So today there are many protocols, what we call application protocols, they are always increasing. And also the fact that you rely on protocol plus port, it is good, but it's not that important anymore. In fact, you see, when you have a known traffic inside Wireshark, you can click in the right mouse button, you can say to Wireshark, okay, decode this as. So you say, this IP and this port, this is the protocol. Okay? This is a typical example, just to overcome this limitation. Statistical traffic classification, basically it is used to classify the traffic using statistics. So people are studying the traffic, how it looks, and they're making assumption that, if it's that big, if the distance, temporary distance between two packets is this, and if that, then it is likely to be this. And many times, these techniques are using machine learning algorithms to learn from the traffic how a certain protocol behaves. In some cases, they are good. They can reach very high reliability, 95%. In many cases, they are very bad. So we don't want to use those. What we want to do, we want to use the same approach as Wireshark is doing. So namely, look at the header and the packet payload. So what we do is the packet inspection. The packet inspection is a technique that inspects the packet payload. And please note that Wireshark is already decoding a big part of the payload. So if you think about SSL, for instance, if you follow an SSL connection, you will see that the initial handshake, or when you are exchanging part of the SSL, the header and everything is already decoded by Wireshark. So this information is there. DPI is a bit dangerous in the sense that you are looking at the content, okay? So you have to be careful when you do that. But you know that before starting a packet sniffer, you must have permission and you must know what you're doing. So this is already part of the story. And usually there are no false positives with the packet inspection because we try to match the protocol for what it is. But at the same time, you have to pay attention because sometimes the protocols are trying to hide themselves. Just to make an example, WhatsApp, okay? The protocol of this popular application changed 1 year ago, 2 years ago, I don't remember, when Facebook has introduced WhatsApp voice. WhatsApp, to hide itself in the network traffic, starts with one protocol, and then later on becomes WhatsApp. So if you look at the connection, at the beginning is not WhatsApp, and then it's becoming WhatsApp. So the fact that you see the initial packets of a connection that look something doesn't mean that this is that protocol. This was a technique also used by Skype years ago. So when you try to enter, or to leave a network to connect to Skype, and the Skype traffic was not permitted, Skype was impersonating another protocol before becoming Skype. In DPI, we don't do just traffic classification, but we also do some metadata extraction. So we also extract some information. We don't have to do much here, because Wireshark is already doing that. So if you look at the HTTP protocol, you will see that the Wireshark is able to extract, for instance, the URL, the server name, and so on. But just to mention that DPI is not just used for classifying the traffic, but also for characterizing the traffic. And information like the server name identification, SNI, and SSL is also very important because it allows us to understand what type of traffic we are observing. Because if I see traffic with a server name of whatever, .youtube.com, this is YouTube traffic, right? So it's not important for us to decode the traffic because this is not our business. We don't want to intercept people. But we want to look at a part of information that we are able to understand and Wireshark is able to decode just to characterize the traffic and then likely to discard this traffic. Like I said before, inside Wireshark, you will see this as an example, there are generic protocol dissectors. So many times when you see SSL traffic, for instance, you will see TLS 1.2. But that's all. It does not go beyond this. It does not say, okay, this is Facebook. Yes, it is TLS, but it is used by Facebook to, connect to Facebook. And then, when you have a protocol, the protocol dissector here is enabled based on the port. So usually, this is what happens. And if this is not the case, then you can suggest to Wireshark to use a specific dissector. And this happens this way. So when you have a traffic that you are not able to decode, you click on a packet, right-click, a window open, decode as, and then you specify the port and then the protocol. And then Wireshark is trying to decode the traffic on that port as if it was this protocol. If the decoding is successful, you will see, the packet decoding. If it is not successful, you will still see raw data. But this is a manual activity. It will be nice for Wireshark to understand that on this non-standard port, we are monitoring net flow instead of going right-click this port, net flow. Okay? So it will be nice Wireshark to be, to try to decode protocols a bit more aggressively than what it is today. But anyway, there are many protocol dissectors inside Wireshark that are already doing a great job. This approach, unfortunately, has some limitation. Because, first of all, the number of protocols is limited to the number of dissectors that Wireshark is supporting. So you cannot have more protocol than the dissector you have. It's not possible to mark traffic using things like traffic on this port from this source to this source is. This is a typical example for protocols that are proprietary, or for protocols that are flowing on non-standard ports. So for instance, a typical example is a monitoring camera. So if you have this camera that is streaming traffic, not using standard protocols like RTP or TCP, but using something else, it would be nice to say, Wireshark, if you see traffic from this IP, that is my camera, on this port, then this is a video stream. Unfortunately, this is not possible. Another thing that is not possible is to say, for instance, if you see traffic, HTTP traffic, towards CNN, this is the CNN protocol. I know it does not exist. I know the CNN protocol does not exist. But it is important because if you have a pie chart of your traffic, you will say, okay, this is CNN, this is the portion of the traffic. If you see YouTube traffic, this is not the traffic you should monitor because it's not part of your monitoring activities. The same for Netflix. These things, unfortunately, are not configurable. The only thing that Wireshark can do is to set a port, TCP, then this is the dissector. Now, we would like to extend this dissection capabilities of Wireshark, and we would like to tell network administrators more about the protocol they are monitoring. So instead of going, decoding, learning something, because Wireshark should be a tool that is more user-friendly than what it is today. So we would like to do, in essence, more than what Wireshark is doing with the current protocol dissectors. Unfortunately, deep packet inspection is one of the things that in the market is more and more expensive. If you look at research or if you ask for a quote, you will see that most of toolkits, first of all, are under NDA, so you cannot use them with Wireshark. They are very expensive, so they make difficult to use them inside our favorite packet monitoring tool. So in essence, you will be locked in, you will be spending a lot of money just to obtain this. Fortunately, at Tentop, we have developed an open source toolkit called NDVI that you can go and see on GitHub. And this toolkit, it is open. We believe that open source is in particular important when you go and read information sent by users. The fact that Wireshark, it is open source, it is not important, it is very important. Because if you want, you can open the code and see what's going on, because this tool is analyzing traffic of the people. And the same here for deep packet inspection. You heard about the security issues that from time to time are happening. So it is more important than for other tools to understand the code and to see that there are no traps, there are no situations that are not very nice. So in essence, NDVI, it is able to detect and to recognize over 200 protocols. When I say protocol, again, I don't mean just TCP, HTTP, protocols that have an RFC. But also I'm talking about protocols that are protocol just because there is an application. Okay? So WhatsApp, is a protocol in the case of NDVI, even though if I talk, from a computer science standpoint, it is not really a protocol. So NDVI is able to decode those protocols. It's a library written in C. It runs on Windows, Linux, ARM, MIPS, whatever. It's portable. It has been integrated in various projects, not just used by us. For instance, there is an NDVI net filter that allows you on small OpenWRT-based devices to say drop BitTorrent, okay, on my router. So this is the type of thing. It is able to analyze plain internet traffic, encapsulated traffic, and so on. So if you are interested in this type of things, I think you should definitely look at NDVI. Now, why I'm talking about NDVI? Because what we have done here, so we have integrated deep packet inspection with Wireshark, not to replace the Wireshark decoding capabilities, but to complement them. So to add something on top of them, okay? To have the best of both worlds combined. So in essence, we want to go beyond IP or port and protocol, when we want to talk about higher application level and allow people to filter on that. Inside NDVI, the protocols are specified as network protocol dot application protocol. So this means that if you make a DNS request to 8888, so the Google DNS, you will see that this as DNS.Google. So if you want, you can filter on DNS, this will be a DNS protocol, but at the same time, you can filter on Google. So if you go to Google Maps, you will see this https.Google Maps. If you say Gmail, it will be https Gmail. For some protocols, there is not this dual thing. So in case of Skype, this is just Skype. Okay? So in the case of Facebook, in this case, you will see DNS.Facebook. In the case of traffic towards Facebook, so when you're browsing Facebook, you will see SSL.Facebook. We are able to decode also protocols such as Tor that are a bit challenging. And for encrypted traffic, we are able to bind a traffic to an application protocol using the SSL certificate name. Okay, so in essence, the idea here is to enable people to use Wireshark to say, okay, give me all the Skype traffic out of this packet trace, okay? Or discard this Skype traffic because it's not really relevant. I don't want to fix Skype problems. I just want to care about my thing. Or for instance, who is using Spotify on my network? These are typical question that maybe you want to give an answer to. The integration of NDVI and Wireshark is something that we wanted to do in a clean way. So in essence, we didn't want to impose that everybody that is using Wireshark has to use NDVI into the library. Because if I would say, okay, NDVI is good, it's giving you an added value, but if at the same time, in order to use NDVI, you have to recompile Wireshark, you use a non-Wireshark built binary, then it's not a good thing, right? So for this reason, we want to make sure that people use stock Wireshark binaries that you can download as part of your operating system or as part of the Wireshark Foundation, and that you are able to use NDVI. So in order to do that, we use something called XCAP, external capture. That it's part of Wireshark since a few years. So in essence, if you go to the GitHub link I've shown you before, you can download this XCAP module called NDVI. And as soon as you install it inside your personal plugins, for instance, unless you want to put in the global plugin of the machine, this is what it happens. You will see that it will appear under your interface here, a new module called NDVI. And from this time, the module will be able to recognize the traffic. So in essence, you will be able to complement what Wireshark has with that. Now, we wanted to do this integration in a way that you don't have to keep in sync the Wireshark implementation or the Wireshark version with the NDVI version. So this means that the tool, the XCAP tool is self-contained, but at the same time you need a Lua file that you have to install, that is part of the project, to interpret the information that the plugin is doing. So in essence, you need two things. One, the XCAP plugin, and two, the Lua file installed. I will now show you how to do that. So in essence, with this XCAP tool, you are able to capture traffic. You can open a packet trace, or you can capture live from an interface, and the Lua script will be used to interpret the information that the plugin returns. Okay? So you have to do an installation of these two modules. So in essence, you go to NDVI, that on GitHub, you will have this NDVI reader. That NDVI reader was designed as a testing application for our library, because NDVI is a library. It can be used, it can be integrated in various applications, but it is just a library. So we needed one application to demo the library, and also for development purposes, just to do regression testing, this type of thing. So you take NDVI reader and you do the installation, and you take NDVI.lua and you do the installation. One is the XCAP module, the other one is the Lua script. So NDVI reader, let me increased. It's a testing application. Now you see at the end, it's adding some XCAP extensions that are recognized by Wireshark to enable it as a module. NDVI reader natively is doing things like this. You specify a pickup file, let's say, here's an example, and it detects the traffic. And if you add V1, it also shows you for this connection, this is the HTTP.Facebook traffic. Okay? Now the idea is to put them together and to integrate this tool into Wireshark, so without using the command line at all. So for the integration, I told you, it's very easy. You have to take the binary NDVI reader, put it into the XCAP folder or create a symbolic link, and to take the Lua file and put it into the .wireshark/plugin directory that you have on your own home directory. And now let's make an example. Okay, let's start Wireshark. You will see that here there is NDVI reader interface. You click. Here you can specify an interface name or a pickup file. This is a capture I've done on the way to here, okay, on my flight. Here you can specify the protocol name. So I told you that NDVI supports over 225 protocols. The protocol name you want to filter. So for instance, if here you specify Facebook 119, it will return to Wireshark only the Facebook traffic. If you don't specify anything, it just returns to everything and classify the traffic. So let's leave, no protocol filtering. And just to start. As you can see here, you will notice that there is something different than before. This traffic is not just SSL anymore, but is marked as SSL.Google. Why this? Because I was trying to connect to Google. So in essence, we have enriched the protocol. The protocol column that you know has now been modified, extended. So we add protocol information. And another thing that you will notice here, there is a new entry. Oh, let me enlarge the screen a little bit. There is a new entry here for NDVI. Like I've said before, this protocol is called SSL.Google. So it means that there are two protocols, 91 that means SSL, and 126 that means Google. As we do development on NDVI basically every day, so you will see that NDVI is currently recognizing a few protocols tomorrow, some more protocols up tomorrow, any more, and so on. So we decided to decouple this from Wireshark. This was very important. In order to do that, we said, let's put all the knowledge inside this XCAP plugin so that we don't have to update and to keep in sync these two applications, because otherwise it would be a nightmare to use. Now I'm going to show you how this has been achieved. What in essence the XCAP plugin is doing is adding a trailer to the pocket. So I know it is not that nice because we are modifying the traffic. But this was the best way we would think of so that we could report this information to Wireshark. And the Lua plugin that we have installed, it is able to understand this. Going back to Wireshark, you see that this is the trailer. Okay, and this trailer, you see SSL.Google, so it's written part of it. Now, it is not that nice to extend the packet that much, just to put the protocol name also in ASCII inside. But this way, we managed to decouple completely the implementation of NDVI and the version of NDVI you're using with the version of Wireshark you're using.
So is that in real time, or is that just after a trace has been generated?
So when you capture live, you extend the packet, so we move the CRC again. So if you are capturing from an existing trace, we add the trailer. So in essence, before the CRC, if any, we put our stuff, and we recompute the CRC.
But that does happen if you're doing live capture too, right?
You can do it in live capture, of course.
So the Right, so you're talking to the NIC. So that point, right?
Oh, sorry. Okay. This is what I'm doing. So now go to Facebook. So in essence, the packet is captured, it's returned by pickup, and before sending it to Wireshark, again, I apologize, but this is the best we think of. We have enlarged the packet a bit, and we have inserted NDVI information.
So you're running that on your laptop, right? So where my mind is going is 10 gig NIC cards. So how fast, what kind of capacities and
Actually, give me a few minutes, if possible. Okay, and then of course, the nice thing is that if you click here, you will see that at the end of the packet, see NDVI protocol proof. Okay, so you can do NDVI dot, this one. Let's put SSL. That's it. So we filter all the rest of the traffic out. Okay? And the Lua plugin is also creating a new entry here. I will be talking about the rest, but let's now focus on this. It gives you an overview of the traffic you're monitoring. So the drop protocol, of course, I went to Facebook. It is Facebook. But you also see the top flow. I understand that this is probably not what you expect from a packet-oriented tool like Wireshark, but from the monitoring standpoint, one of the first things that we want to know, who are the top talkers, okay? What are the top flows? What is the main traffic that you are seeing? So this is the thing. One of the limitations I'm not able to fix is the following. So I wish I could click here and say, okay, now give me all the SSL.Facebook traffic. But I probably will talk with the developer so that it is possible to have here URLs so that I can set a filter. At the moment, this is not possible. Now, so in essence, we have extended the traffic, so the payload, in essence. At the end, so we have put this information, we have put a magic just to make sure that we don't go in conflict with X, GigaOn, and other companies that are using the trailer just to inject information about, for instance, the port or the precise timestamping. And then the Lua module is interpreting that. So the pro is that everything is clean. You can compile it to Windows, works. The con is that, of course, we are extending the packet. So if you do save as, you will save this on disk. But again, I think it's a minor drawback. And the Lua module, it is responsible for interpreting this information and for rendering on the screen. And then you will see reports like this I have shown you before. So either during capture or at the end of the capture, you go and say, show me NDVI, and this is a report you will see. So if you have an unknown network, you have an idea of what is the type of traffic you are trying to monitor. And of course, like I've shown you, it is possible to go in the filtering entry and put your own protocol name. Again, this is all free, all open source, no cost, so you simply can use it, and it is integrated currently in Wireshark, and you can use it, you see, it is naturally integrated through Lua. So at the end of your window, you can also see how to filter traffic. Of course, usually people filter based on the protocol name, so you see http.google. But if you know the correspondence between the protocol ID and the value, you can also use the numeric values. So the thing is that if you know in advance what protocol you want to use, you can tell the XCAP module, okay, give me this protocol. Otherwise, you say, give me everything and characterize the protocol. Like I've shown you before, we have more than 200 protocols, so the list of protocols is pretty long, it is growing. So from time to time, make sure you recompile, you update the XCAP module. And if you use the binary packages that we're building, so similar to what the Wireshark Foundation is doing, and if you do an APT update or a UM update, from time to time you will have all this installed. And by the way, you don't have to move any file. So if you use our binary packages, we are already storing the XCAP and the Lua file at the right place. So you simply have to install the binary packages from us if you don't want to compile it yourself, and then start your Wireshark on Linux, and then everything will be done automatically. Okay, so there are a few limitations, but that's not the real thing. Now what I want to say is the following. Now we have NDVI. Now we want to go faster. So this was the question. How can we combine 10 and 40 gigabit or 100 gigabit in this? So how can I say to my system, okay, I want to have the best of both worlds, and also get the files somewhere else. Now, at the last Wireshark conference, and this is a GitHub entry, so we have introduced a tool called NTOP dump. So this XCAP module is doing exactly like that. And this time, I want to show you an improvement of that version. And why is it better? First of all, because we have created another open source technology that you can find here on GitHub called NDVI. So I think everybody is familiar with these filters, okay? You can say TCP and port. But the thing is the following. If you have a modern card, like one of those network adapters I listed here, the card itself is able to filter this traffic. But unfortunately, the operating system does not understand that. So if you have an FPGA-based card and you want to filter on port 80 out of 100 gigabit link, it doesn't work. So simply, all the packets are returned to Wireshark. Wireshark is overflooded, and the filtering basically will return just a subportion. Instead, NBPF is a tool that transparently translates the BPF expression to the native filtering capability. So it means that, just to make an example, if you have a 100 gigabit link, if you have, let's say, an Accolade, Intel, an Apatec, whatever card, you say, start Wireshark, you say, IP this, okay, start, Wireshark through the NTOP dump module understands that, sets the hardware filter into the card, and your system will be receiving only the packets matching this filter. Because, unfortunately, network adapters don't understand DPI, you cannot say, give me all the Facebook traffic. But at least you can reduce significantly the amount of traffic you receive filtering in hardware, so without packet drops. So in essence, with 10 BPF, so we are moving the hardware rules inside the NIC instead of doing them here in user space. Okay? This is the main thing. Now, what we have done in the past few months, so we have improved this with remote SSH. So you know that inside Wireshark you can do a remote SSH capture. So you can go to a remote port. Now this NTOP dump, it is able to do a live capture remotely, combine NDPI, and at the same time, if you have packet traces from you can find the storage, and you're using the indexing tool that NTOP is using, you can also filter based on time on those traces. Unfortunately, I don't have a Linux box here, but I brought here some movies just to demonstrate this thing. So in essence, you click on this remote interface, you set a simple filter. So this filter will go in hardware, okay, if you have that capability. You specify the host you are connecting to. So if you are here, you have your probe, let's say in Canada. So you want to connect to Canada, this is done through SSH. So it's very similar to the SSH plugin that we are very familiar with. You click on Enable NDPI inspection. So it means that the packets, when they are returned, they are also NDPI inspected. You specify the SSH user and password, and then you do start, and then you will be connecting remotely to the box through SSH, so safe, and do standard capture, and then packets are coming, and you will see that the packets are marked here with the protocol name. Okay, so you can do usual things that I've shown you before. So.
Now, what about the VM? So when you're doing that remote, you're remote session, does that suggest that the NIC at the remote end has to be capable of supporting NDVI?
No. So in essence, this plugin is opening an SSH connection to the remote session. So we do packet capturing with RPF tools. They understand there is a BPF filter. The BPF filter is set in hardware in the NIC, and before the packet is piped back to our tool, we do pipe NDVI reader and filter. So no, the NIC does not have to understand the NDVI. So another example. It's a similar example but with a pickup trace. One of the tools we have developed is the ability to continuously dump pickup trace at high speed or long, we're able to dump up to 40 meters. Now, the thing is that here we have something called timeline. So while we dump the traffic, we also generate an index. An index contains metadata. So we have the MAC address, we have the IP, we have the port, we have the application protocol. And this is what I'm showing now. You can set a time, okay, say in this time window, give me all the packets I'm interested in, so simply don't go one packet after the other. So like Wireshark, unfortunately, it is doing, but go directly to the goal. So if you specify BPF filter, then go directly to that. Yes, so you can do a packet extraction remotely. So again, SSH, time window, extract the packet, send them back, and pipe them to NDVI reader. And do the standard things that we are able to. So, just to recap a little bit, we are now able to understand application protocol. We are now able to combine this with remote capture. So if you have a wide area network, so we're able to do that. So if you have a machine that is continuously recording traffic, if somebody is calling you, say Monday morning from 8 to 9, there is this problem, okay, you can go and SSH, not typing anything, but simply clicking on Wireshark, remotely extract traffic, and characterize it through NDVI. Okay? Thanks to the high-speed packet capture that we have on PF Ring, and thanks to also to the hardware adapters that are accelerating that in case you have one, it's also possible to do this transparently and put the BPF inside the card. If you don't have this capability, filtering still happens, but in software. So expect packet drops. And also you are able to extract terabytes of pickup very, very quickly, because you don't have to go one packet after the other, but you simply go to the goal. So I'm going to skip this slide. So in essence, the first part of the talk is over. I demonstrated that it's possible using the stock Wireshark you can find in Ubuntu, CentOS, or Windows. You can characterize the traffic with layer 7 capabilities. You are also able to do a remote capture using NDVI, so that you have traffic that is now characterized, that can give you a better overview of what is happening. So if you are on an unknown network, like here, for instance, if you start capture, you will be able to characterize the traffic with application protocol. Now, this is one part of the story. The second part of the story is actually a work in progress. I wanted to extend the Lua script I just made to demonstrate that it is possible to turn Wireshark into a more monitoring-oriented tool. So I don't want to jeopardize the engine. Actually, Wireshark is perfect because it's already decoding all the part of the protocols, all the fields I'm interested in. So I just want to demonstrate, and I hope that somebody can contribute to this, not just us, to extend this even further, so that you are able to see more in detail what is happening on your network. So what you will be seeing now are simple examples of what are the activities I usually do when I have a network that I don't know. So just to have an idea of what is happening. But again, this is a work in progress. It could be extended and be in many ways and add a few things. So in essence, I want to have the overall picture. The overall picture is what is missing. Okay, Wireshark is perfect for exactly decoding the protocol, exactly interpreting a specific byte. But it's not that good when you want to see what's going on from 1 kilometer high view. So we have rich packet level metrics, fantastic. But we also have a powerful language, Lua, that is able to glue this information. I don't want to give you a tutorial on SCAP or Lua scripting. If you go to the past editions of SharkFest, you will see a few tutorials on this matter. I just want to explain you what is possible to do in Wireshark. All the things I will be showing now are being installed under the tools menu. So as soon as you put the NDVI Lua module, you will see this menu will be populated. There are some new entries. So at the moment I just covered the NDVI one. I will now describe a few others. But again, these are simple examples. Okay, you can add many more, and I hope you will do that. This software, again, is available free of source, free of charge. It's available as part of NDVI. If you want to know more about Lua scripting, I suggest you to have a look at this talk. Now, problem number one, VLAN. Many times people install switches, don't care about the VLAN, say, forget transport, everything, okay, transport. This can become a source of a problem. Now, if you have a trace, okay, you are able to click on packet by packet and see the VLAN ID, fine. But then, you don't have an overview of all the VLAN tags on your traffic. So you cannot expect that people will click, packet by packet. So why VLAN are important? First of all, I want to know if there are VLANs I don't expect on my traffic. So if I expect VLAN 5 and 10, I say also VLAN 15. This can be a problem. Okay, but filtering with not this and not that is kind of not very convenient. I also want to identify invalid VLAN configurations. So one of the things that we have done here is this. So if you take some traffic that is VLAN tagged, you can go here on Tools, VLAN, and you can have an overview, okay, of all the VLANs that you can see in this traffic. The script is very simple. Whenever a new packet is received by Wireshark, you have a hash that is incremented with the VLAN tag. So in this way, you can see if all the VLAN you see on your traffic are those VLAN you expect. Because again, this can be one source of the problem. Again, these are simple examples to demonstrate the power of Lua and Wireshark. The second problem is hardware. For many years, network monitoring tools didn't pay too much attention to layer 2. If you think about NetFlow, for instance, it's a pure layer 3 technology. Layer 2 is just, for moving packets in a LAN. That's not really true, because these days we see that the Internet of Things is becoming more and more important. You see there are many tools that are monitoring ARP, because ARP is an important source of information. You see that there are the router, especially home routers, that are constantly doing ping through ARP, just to understand if the device is up or not. Okay? So it's important to monitor ARP. But again, we cannot go packet by packet and to see what's going on, because Wireshark has ARP monitoring tools, but they're not designed for monitoring, but they're more designed for inspecting ARP traffic. So in essence, what I would like to understand is the following. I would like to open a pickup trace and to see who is doing what. And to see, for instance, why a certain host is sending so many ARPs. This is an ARP scanner. I know that, I believe, most of you are familiar with the tool called ARP. So monitoring ARP traffic is not something that we should forget. It's an important protocol, especially these days, where you have intruders that are coming to your network, or there are many devices that are connected to your network, like a television and so on, that can become a problem. So in Wireshark, again, similar to what I've done, you click on ARP, you open ARP, get tools, example, here you see ARP, and this is doing an inspection, okay? So I see that this, the first ARP, it's 00, so it's a special address, and I see who is generating most of the ARPs, and what are the hosts that are participating in my network. But ARP alone is not enough. Sometimes you want to combine with IP, because, for instance, counting the number of occurrences of IP and MAC you can realize how many IPs are behind a certain MAC. A typical example, if you want to identify a router, so I don't know what is the router here, or who is routing the traffic. I mean, I can look at my next tab to see what is the router that has been assigned to me. But how do I know if there is somebody else on my network that is using another machine for routing? Or for instance, counting the number of queries of IPs per certain MAC, I can also figure out more information. For instance, I want to know how many virtual machines are running on my network. Of course, you can modify the MAC address on your VM, but counting the number of parallels, VMware, MAC addresses, it's an interesting activity for trying to figure out this information. So, this information is very important, so you don't have to consider them unrelated, so an IP and a MAC. So they live together. Okay? So the cardinality, it is important. So if you look at the MAC, a nice thing about Wireshark, it is also able to resolve the MAC address here. It's possible also to give an idea of the devices that are running in this network, especially here, especially with those protocols like MDNS or SSTP that are broadcast oriented. Start Wireshark in this room and try to see how to do, just curious, how many iPhones, how many Samsung here, and so on. This is a typical activity. So in this case, you can see that your network is used mostly by mobile devices simply looking at the app. Or for instance, why there are so many hosts behind this zigzag? Because this is probably the gateway. But if this is not the gateway, there is a problem. And you have to figure out that there is a problem with the network. Or for instance, why there are so many IPs behind this Apple Mac. So this is an interesting activity. Again, it is very simple. You simply have to keep a hash. So whenever Wireshark sees a packet, I increment a counter here, counter there. But the result, I think, is very interesting, at least from the monitoring point of view. Because without knowing too much about the network topology, I know that this is to be a gateway. Well, zigzag also means that. Another example is DNS. In many companies, you should be forced to use a certain DNS, okay? The company DNS. You should not use the OpenDNS or Google DNS. Right? So unless you enforce it on the firewall, you can tell your folks that they should not use that, but you are not that sure, right? You cannot go packet by packet inside the DNS to find out what you're doing. Of course, you can go under statistics DNS, but these are mostly related to response type. They are covering another part of the problem. And you know that the DNS resolution is an iterative resolution. Okay, first of all, you go to the root DNS, then you go to the DNS of your domain, and then you go to the domain DNS, and then you resolve the real IP. So, I mean, you need to pay a little bit of attention analyzing that traffic. And also these days we are facing with DGA, domain generation algorithm, especially for ransomware. What are they? If you go to Wikipedia, this is a link, you will see that the DGA are used as rendezvous point for malware. So in essence, it's an algorithm that based usually on the date, generates a string that is not very nice. It's an ASCII string, doesn't mean anything. But that means that if this ransomware wants to talk with the master, today he has to use this name. So instead of hard coding the IP address inside the binary, you simply use this algorithm. So even if you dissect the binary, you cannot find that. And we have seen an example of this. So let me show you a demo. Again, nothing really special. So I decode the DNS traffic, and then you go here, you see DNS. Now, this is the thing. So, am I supposed to use the Google DNS? I don't know. Most of the traffic is going there. As you can see, if you will use 192.168, 1.1, I see error. So probably this is not good DNS I should use. So finding this out and trying to find the client who's using that DNS, it is also very important because I can see if there is a misconfiguration. Then you can see the probability of the client, so those who are resolved addresses, and then the resolver, those are resolved. And then you will see my queries. It's very easy, okay, inside the Wireshark to see what is your query about, but it is not that easy to go one by one, especially if you have a long trace. It is very easy, in very nice from a point of view, to see immediately what's going on. Especially if somebody is trying to go to Facebook, and see some robots, and so on. Especially if you have a long trace, that is very important because NDVI, the NDVI.Lua is showing you the top names, so you can figure out where your people are going. And the same for SSL. The SSL certificate name that is decoded by Wireshark is used, for instance, by NDVI for understanding who are contacting. So, are we talking with YouTube or are we talking with Google Maps? Okay, because this traffic is all encrypted. And it's also important to know that if there is no server name, then this means that it's a connection that might be special. So sometimes you use SSL to connect back home to OpenVPN, for instance. And this is an indication of maybe a problem. Maybe somebody is trying to circumvent the security. And the Lua plugin is doing exactly that. So let me show you an example. Well, let's take let's take Tor for instance. This is an example of Tor traffic. You see Tor, okay, it's a special protocol. You know what it's about, right? So it has its own protocol is connecting the starting entry point just to enter the onion ring network. But you can also decode and detect Tor simply looking at these are DGA, so domain generation algorithm names. You will see they are not meaningful. They don't mean anything. They are not Pittsburgh, Luca, or Wireshark. They're just letters. But that's not very important. So when you see this type of names in SSL, start to think if this is Tor, or if you see those names inside the DNS, somebody has a malware. Is trying to contact the master host. So start inspecting those clients because there is something wrong here. Now, the last thing I want to show you before completing is something that is more interesting for us that are doing network monitoring. Latency. Okay. Suppose that you have a network. So suppose that you have a Wireshark somewhere in the middle of the network. Suppose that you're observing traffic from one client to the server. So I see some of my users here are accessing Facebook. I want to know the latency. As you can see here, it's possible monitoring the scene and ACK flags, but you can do the same also at the end of the connection. The red line here, so it's the time it takes from the scene to go from the Wireshark observation point to the server and back. So this is the round trip time, RTT. And this is the client RTT. Okay? If I monitor my network latency throughout the day and classify it for per autonomous system, I know how fast I can reach Google during the day. So if it's stable or if it's changing over time. And then, in addition to that, I can do the application latency. So in essence, the first metric I've shown you is the network latency. So how long it takes a packet to go and come back. Fine. And this response is sent by the IP stack. So in essence, the remote machine that's replying. Here, the application latency is the time it takes, or call it application delay, the time it takes from the get slash until I see the response back. Okay? And of course, I have to take the application latency minus the server latency, and I have the real application latency. This is an important metric for those who are doing network monitoring because I want to see how fast the server responds. Of course, some of the servers are fake, so in essence they start sending back a reply and then I have to wait because the rest is not coming that fast. But again, it's a good indication of how fast the system is going. Let me show you an example. Even a more example. So this is a scene, okay? And this is a synapse. You see here we're putting the server latency from client to server. Now this is a simple packet in a simple example where I see the synapse right after the scene. But in general, if you are sniffing from a link from a tab, you will see the scene, many other packets, and then many other packets, and then so on. So the software is taking care of this problem. Okay, so they don't have to be one after the other. So this is the server latency. Then if you click here, you will see this is the client latency, so the round trip time. If you're monitoring this over time, you will see also some interesting metrics. This is the get. And this is the application latency, so 300 milliseconds. So if you go here in the menu, if you want to monitor the application latency, you will see that this is the minimum and the maximum latency. And if you are doing that for the network, you have the same. Okay? Of course, the closer you are to the client, okay, the less is the latency. Now I'll show you an interesting example. This is a packet capture I have done. While flying, I was using this airline called Norwegian, so I was up in the air. So you see, these are the latencies, but in essence, I'm speaking with my servers that are close to me. Instead, if you have real traffic, or let's say this fake traffic, I don't know. Yeah, you see there is no latency because there is no scene, so this was the trace I showed you before. So in essence, what I wanted to say? I wanted to say the following thing. Wireshark is a great tool. It is good, but it is packet project. Here I show you how to complement what Wireshark is doing, so extend Wireshark beyond its original design with protocol information, so you're able to filter, packet traffic, say, give me all the Skype traffic. You are able to introduce metrics that are relevant for those who are doing network monitoring. And I'm showing you some examples, ARP, VLAN, IP to MAC monitoring, so that are interesting for security, for monitoring, and so on. My goal today was not just to say, okay, by the way, there is this that you can use and it's free of charge. It's also to stimulate you to have a look at the code that is very, very simple and to extend it beyond what I've done here, because Wireshark is doing the dirty job. So everything is the code about Wireshark. You simply have to pick this field and this field, remember into a hash table, and then to monitor that and to report this through a simple menu. Okay? All the software is available here on GitHub, and I hope you will be using and send us a feedback. Thank you very much.
Thank you.